Okay, let us take two important cases. First one is case 1. The area element is kept perpendicular instead of area element is better. Okay, kept perpendicular to the direction of the field. Try to understand element. This is what it is, a surface. These are the strips. This one particular portion is called element. Okay. Then the area is concerned. The area is taken. The area of this element is taken, and a direction given to it is normal to the element. Normal means perpendicular to the element. Then this area and the direction gives a vector that's called area element vector. Simply element means this particular portion. Okay, element means this particular portion itself is called. So this is the one surface area. One small portion of that element, a surface area is taken. This is the element actually. This area delta S and this direction perpendicular to the element is together will be taken as a vector. That vector is called area element vector or simply area element. Okay, this is delta S bar. Okay. Therefore, if the element is kept perpendicular to the direction of the field, then let us take if. Then theta is equals to 0. Why theta is equals to 0? Look at the figure. This is the direction of the field. The element is kept perpendicular. I told you kept perpendicular means the element is kept like this. This is the element, this is the direction of the field. Now the element is, this surface area of the element is perpendicular actually. But what is the direction of the delta S bar? Delta S bar is this one, this is E, and this is delta S bar. The direction of the element is actually normal to the surface. It is perpendicular to the surface. No, it is perpendicular to the surface. It is perpendicular to the surface. Is a perpendicular mark? No, it is perpendicular to the surface. Therefore, perpendicular to the surface. Therefore, what is the angle between delta S bar? This is delta S bar, direction of the area element. Delta S bar. This is the delta S bar, and delta S bar and E bar are what? Parallel. Then theta is equal to the angle between the parallel. Theta is the angle between the normal to the area element and E bar. No, in the definition it is taken. The element is actually kept perpendicular to the direction of the field. This is actually perpendicular. The field is in this direction, and element. This is the element. This is the surface of the element kept like this. Now, what is the angle between the direction of E bar and this surface is 90 degree. Means element is kept perpendicular to the what it is direction of the field. What is direction of the field? This is E bar. Direction of what it is area element delta S bar. Now what is the angle between these two fingers? This is the normal to the element. Therefore, it is the direction of the what it is area element vector, and it is the what E bar. Both are parallel. Therefore, theta is 0. Theta is 0. So therefore, flux delta pi is equals to it is delta E into delta S into cos theta. Delta pi is equals to E into delta S into cos theta is cos 90. Cos 0, theta is 0 in this case. Theta is 0. Therefore, delta pi, theta is the angle between E bar and normal to the area element. Okay. Delta pi is equals to E into delta S. This is the maximum flux. Passing through an area element. Okay, means more number of field lines are crossing the area element if the element is kept perpendicular to the direction of the field. This surface is kept perpendicular to the direction of the field. Then more number of field lines are crossing this element. Flux is more. field lines. Flux is nothing but it is a quantity which is proportional to the number of field lines. Means it depicts the number of field lines crossing the one particular area element when the area element is kept in an electric field of certain configuration of charges. Okay. This is the maximum flux. This is the maximum flux. Maximum flux crossing an area element. Okay. Crossing an area element. Therefore, delta pi max is equals to maximum is equals to E into delta S. Okay. Case number 2. If the area element is kept parallel to, if the element, simply not area element is kept parallel to the direction of the field, then theta is equals to 90 degree. Then theta is equals to 90 degrees. How it is? I will show with the help of the figure. This is the direction of the field, say E bar, and element is kept like this. Okay, parallel. Okay, surface area of the element is kept parallel to the direction of the field. This is the direction of the field. This is the direction of the field, and the element is also kept parallel. That means surface. This is the element. This is the element. This surface area of the element is kept parallel to the field. Then what is the angle between what it is? So actually theta is the angle between the normal to the element area. Okay, normal to the element in surface of the element. Normal to the surface. This is the surface of the element. No. So this is the direction of the field. And theta is actually in this case, in flux case, E into delta S into cos theta. Cos theta is the angle between this normal to the surface of the element and the direction of the field. Okay, therefore theta is what? 90 degree here. Theta is equals to 90. So this is the what? Delta S bar. Okay, therefore theta is the angle between delta S bar and here theta is equals to 0. Okay, theta is the angle between bar and delta S bar. Here is delta S bar. This is delta S bar. Okay, therefore theta is equals to 90. Therefore flux pi is equals to flux delta pi is equals to E into delta S into cos theta. Theta is 90 here. E into delta S into cos 90. Cos 90 is 0. Therefore E into delta S into 0, cos 90 is 0, that is 0. That is, this is the minimum flux. No flux is passing, no field line is crossing the area element. Simply grazing the surface, not cutting only. Simply grazes the surface. Okay, of the surface element, sorry, area element. Okay, the field lines are not crossing, cutting this area element. It's simply crossing. Sorry, simply grazing the surface. No cutting is there. Okay. That is, this is the minimum flux. This is the minimum flux. Minimum flux. Crossing or cutting. Can be the word crossing or cutting. Cutting the surface element. Okay. Cutting the area element or surface element. Okay. Area element. You can call it a surface element also. Therefore, delta pi minimum is equals to M means minimum is equals to 0. Okay. So, if the element is neither parallel nor perpendicular, then it is kept at an angle theta. Neither element is kept neither parallel nor perpendicular. It is kept at an inclination theta. Element is kept neither parallel nor perpendicular. It is kept what? At an inclination of theta. C bar, this is delta S bar, then this is theta. Now, in this case, what is the rate of flux? delta pi equals to E into delta S into cos theta. So according to the theta value, so in this case the element is neither parallel nor element is neither perpendicular to the field direction nor parallel to the direction of the field. In this case the element is at an inclination of theta to the direction of the field E bar, then flux through it is E into delta S into cos theta. In this case its value is in between maximum and minimum. It will be neither maximum flux is in this case neither maximum nor minimum. Okay. Very simple concept it is. Suppose water is flowing. Okay. Water is flowing horizontally. You are holding a tube. So the tube is what it is. The cross-sectional area, this is the cross-sectional area of the tube, say, is kept perpendicular to the direction of the flow. Flow is like this. This is the tube, okay, this is the tube. This is the cross-sectional area of the tube hole. Then this hole is kept, this is the element, cross-sectional area element. This element is kept, what it is, perpendicular to the direction of the flow. Then more water is entering it. So more water emerges out. So suppose what it is, the hole is, area element is kept in this direction. So then water is flowing like this. Hole is here. In this case, hole is parallel to the direction of the field. The hole means this cross-sectional area of the pipe. Pipe is like this. Pipe is like this. Okay. Water is flowing like this. The cross-sectional area of the pipe is what? Kept on here. This is kept perpendicular to the direction of the flow of water. The more water enters the what it is, tube, and more flow of water will be there, more quantity of water flows in this case. And suppose the water is flowing in this direction and you are keeping the pipe like this. This is the pipe. This is the cross-sectional area of the pipe. In this case, cross-sectional area of the pipe is parallel to the what it is. This area element means cross-sectional area of the pipe. This is the pipe. Is parallel to the direction of the flow of water. Then no water enters the pipe. Then automatically the flow of water will be zero. Quantity of water flowing in the tube is zero. Like that, from the same concept. So now coming to the three more physical quantities. So linear charge density, and another one is surface charge density, another one is volume charge density. Okay, I will give the definition of all the three one by one. Then after completion of all three definitions, then let us take Gauss theorem, last section of electric field, Gauss theorem. Okay, a linear charge density. Linear, first definition, linear charge density. The symbol is lambda. It is the charge per unit length of a wire. The charge per unit length of a wire, it is the charge per unit length. Unit length of a wire. Charge per unit length of a wire. What do you mean by charge per unit length of a wire? Suppose here is a wire, say, okay, and it is charge 1. The wire is charged 1, and suppose it is either positively charged or negatively charged. Either it is positively charged or negatively charged, and the total charge is Q, say, and charge here it is length is L, say, and what is the charge per unit length? Q upon L. Okay, charge per unit length is Q upon L. That is the charge density. But so in the textbook it is not taken simply Q upon L. So what it is, a small line element is taken. This is the wire, a small line element. You can call it a line element. Small section of the wire is taken. This is called line element. If area is taken, area element. Volume is taken, a small volume of a huge volume is taken. Here is a huge volume. A portion of that volume is taken. A portion volume of that huge volume is taken. Then that portion of volume is called volume element. Okay. So here is the small, what it is, area line element is taken of this wire. Then that is delta L, say, that length is delta L, and it contains the charge delta Q, say. Then we can define the linear charge density of a wire is delta Q upon delta L. Linear charge density is the charge per unit length. So it is the delta Q upon delta L also depicts charge per unit length. Okay. Linear charge density lambda, symbolic lambda, it is the charge per unit length of a charged wire. Better to say charged wire. Okay. If the wire is charged, then use the word charged wire. Therefore, lambda is equals to delta Q upon delta L. What in your CBSE textbook, this delta Q and delta L explanation is given technically. You have to use the technical what it is, interpretation of delta Q and delta L. You have to suppose it is an important derivation definition. This now ask this definition. That's why you use the technical explanation of this delta Q and delta L. What is delta Q? Delta Q is the charge contained amount of charge in what it is, macroscopically small line element. Means macro and micro, 2 point. Macro means large scale, micro means small scale. First year you are studied macroscopic phenomenon, microscopic phenomenon. Nuclear phenomena are microscopic. So you know the phenomenon takes place at the celestial level. So universal level, that is the macroscopic. Macro means large, micro means small. Delta L is a small area, macroscopically small line element. Means, so as compared to the entire line, big line, long line, this what it is? This area element is line element is very small. Line element. Portion of a line is line element. Portion of a surface area is area element. Portion of a volume is volume element. Try to understand what I mean by element. And this is the charge contained in. The charge contained in. Charge contained in. So how much charge is there in this line? In this element of the line. So that is the delta Q. Delta Q is the charge contained in macroscopically small line element delta L. But this delta L, even though length is small, it contains a large number of what it is, charged constituents. This particular small charges are electrons and protons. No, electrons are negatively charged, protons are positively charged. It contains large number of what it is, charged constituents. Charged constituents means electron is a charged constituent, proton is also a positively charged constituent. Even though the length is small, it contains large number of what it is, charged constituents. Means charge carriers. They are charge carriers, electrons and protons. Large number of, microscopically large number of charge constituents. As compared to microscopic level, it contains large, even though delta is very small, it contains large number of charge constituents. It can be electrons or protons or any other charge carriers. Okay. So delta where? This is the technical interpretation. Delta pi and the delta Q. So delta Q is the charge contained. Charge contained means charge. Charge contained is charge. Is positively positively charged or negatively charged. The wire may be, it is wire. A portion of the wire is wire element. Delta Q is the charge contained in macroscopically small area element. Delta L of the wire. Explanation for delta L. Delta L should be given, then only it is complete. The definition is complete actually. Element delta L of the wire which contains large number of microscopic charge constituents. Which contains large number of microscopic charge constituents. Charge constituents. Electron is the charge constituent, proton is the charge constituent, holes are the charge constituents, like that. Okay. So delta Q is the charge in this particular line element. This line element actually, as compared to the large scale, it is very, very small in the meaning of microscopically small element, line element, small line element. Okay. So the line element delta L. So this delta L is very small as compared to the microscopic level. But even though it is very small, it contains large number of small microscopic charge constituents, because electrons, protons, these are all microscopically very, very small elements. No? So microscopic charge constituents. Try to understand the SI meter of lambda is linear charge density is linear charge density. Lambda is unit, is simple. It is charge in coulomb, length is in meter. Therefore, coulomb meter. Okay. Coulomb meter per meter. Coulomb per meter. Meter. Another one. So linear, same definition. Surface charge density. Second one is surface charge density. Same. Okay. Surface charge density. Charge density. It is denoted by sigma. Am I went wrong in symbol? Let's see. Wait for a minute. My doubt is whether I went wrong in this. In the symbol, linear charge density delta Q lambda, correct? Okay. It is here is sigma. It is not rho. It is sigma. Okay. Sigma. Volume charge density is rho. Volume charge density is rho. It is the charge per unit surface. Unit surface of a charged surface. Okay. Of a charged surface. Means here surface is charged. Okay. A particular surface is charged. This is the surface S is a. Okay. This is the surface element delta S. And it is either positively charged or negatively charged. This surface is either charged positively or negatively. I have taken a charge surface element here. This is delta S. It contains the charge how much? Delta Q. This is delta S. Delta S. It contains the charge how much? Delta Q. Then charged surface, and it is denoted by symbol is sigma. Sigma is delta Q upon delta S. Same. Where delta Q is the charge contained in microscopically small surface element. Area element also you can take surface element. It was area element or surface element. Delta S of the surface which contains large number of microscopic charge constituents. Okay. SI unit of lambda is, so it is coulombs per meter square. 5 meter square. S is in area surface area. Area is in meter square now. Coulomb per meter square. Square meter. Okay. Square meter. Okay, last one. Suppose here is a volume. Third one is here is a volume. Volume is a enclosed surface. That inside that one, some volume of what is quantities is there, say volume of a certain quantity. Suppose the air filled in a football, then the amount of air inside the football itself is the volume of the air. Okay. So here is a closed surface, and the inside space itself is called volume. In this particular volume, charges are there. Okay. Charges are stored. Okay. Then a small volume element. charge delta Q. Let us define the charge per unit volume now. The charge per unit volume is called volume charge density or simply charge density. Simply charge density means it is the volume charge density. Okay, volume charge density. Its symbol is rho. For this one, symbol is rho. Okay, rho. It is the charge per unit surface. In the previous definition, it is the charge per unit surface area. I have unit surface area is the word area is listed in the last definition. So you include that word unit surface area. Here it is the charge per unit surface unit volume. Charge per unit volume of a charged particles of a charged volume of a charged volume. It is the charge per unit volume of a charged volume. So one big volume is there. That big volume is totally charged. V. And here is the what? One small volume element is taken. This is the delta V. And the charge inside it is delta Q. Okay, delta Q. Therefore, sigma rho is equals to delta Q upon delta V, where delta Q is the charge contained in macroscopically small volume element. Volume element. Understood the element? A surface is taken, a surface area is there, and a small portion of that surface area is area element or simply surface element. Okay, a wire is there, a conductor wire is there, and a small element of that wire is taken, then it's called line element. A big volume is there. A volume is one which it is an enclosed, what it is, a space, a closed space, you can treat it as a volume. And in that volume, a small portion of the volume is taken, then that volume is called volume element. So delta Q is the charge contained in macroscopically small volume element of the volume. This is the entire volume V of the volume, which contains large number of microscopic charge constituents. Okay, understood? SI unit of rho is what? Volume charge density or simply charge density. So it is delta Q is in coulombs, volume is in meter cube per meter cube. Coulomb per cubic meter. Meter cube. Okay, meter cube or cubic meter, one and the same. This is with help of all these basics: flux, surface charge density, volume charge density, then linear charge density. Linear means line. Okay, so charge density. Let us go to the last section, that is the Gauss theorem. So 3 applications are there. On those 3 applications, one application is definite for examination derivation. Okay, and one important definition derivation is left out, that is torque acting on a dipole. Tomorrow I will take the torque acting on a dipole.